So we don't have that much time, so the hint I was trying to get out was this. You know, let's say you were reviewing your Chem 1A, and then maybe this is a lot fresher in your memory than not, but you know, there was this equation. Do you remember this one? P plus NA over V squared, V minus NB is equal to nRT. You guys remember that equation? This is the van der Waals equation for a real gas, right? Have you ever tried to solve the van der Waals equation for V? You get a cubic, you know, V cubed, it would be AB cubed plus V squared plus CV plus D is equal to 0 or something like that, right? You remember this? Oh, I don't know if you did this in your homework. Maybe not, maybe yeah. But in Chem 1A, at least my Chem 1A students, I was hoping that something would click. Oh, I've tried to solve a cubic before, right? But what happened? It's just, it fades from your memory, right? Because we did this, solving the cubic. And how did we do it? We didn't do it like your normal algebraic way where you get the correct answer, right? We used approximation methods to solve it because the math is just beginning to become a pain, right? But this goes to the point that think about this, you know, 3 years, 4, whatever, 2 years, 3 years, 4 years later, you're ready to take the MCAT, you go to your chemistry friend and you ask them, hey, can you help me with the MCAT? Right? And then, what do you think? No way, you know, there's absolutely no way. You need to take a year or 2 or 3 off to review everything because you've forgotten everything. And so what you want to do is you want to try to keep it fresh in your memory and tell me, you know, going through 100 pages of notes is quick. It's easy. You've read it so many times. It's like ingrained in your memory. By the time the final comes along, you don't even need to study it. You've memorized the whole thing, the whole course, you know? And anyway, getting back to this. So what did we use to solve this? Now, Scott remembered, it clicked, but you guys remember the method we used? Yeah, we used Appendix A, and rather than call it guess and check, you know, the guess and check is taught in elementary schools, right? Guess and check method. It's we call it, we don't call it the method. It's the exact same method, but we call it the method of successive approximations. Method of successive, and essentially it's guess and check. So 2x is equal to 6, and so you start guessing some numbers. You know, let's say you guess x equals 2, and then what you get is you get 4 is equal to 6, so it doesn't work, right? It's too small, So go up to 2.5, and you get 5. And go up to 3, and you got it. You know, in 3 guesses. And so it's the guess and check method. And so the guess and check method, sometimes a lot quicker than trying to figure this out, right? Itself, and you know, we're going to get a lot of complicated, you know, the cubic, you know, 4th order, 5th order, 6th order equations. In this chapter, chapter 15, we have x cubed, not x cubed, I'm sorry, x to the 6th. You know, what do you do? X to the 6th, something like that. Or maybe you can factor it out easily. And so this is why I gave you 10 minutes, because in 10 minutes you probably could have come up with enough guesses. Maybe you couldn't have, because you know the first guess is tough, right? What are you going to guess for the first guess? You know, I don't know. Well, we know there's limits for x. X has to be between. Yeah, x has to be what? Greater than 0, but less than 0.1, because if x was greater than 0.1, then we'd have 0.1 minus 0.1 would equal 0. But if we had, let's say, x of 0.2, 0.1 minus 0.2 would be negative 0.1. If somebody asks you, can you make a negative 0.100 molar tin solution? Is that even possible? Or somebody says, hey, you know, I'm on a diet, you know, can you add negative 10 grams of fat? or oil, you know? It just, there's no such thing. And so we cannot go negative, so x has got to be between these two. It's got to be greater than 0 and less than 0.1. And so just take a guess. Well, the guess is, you know, Kc tells us some information. Now, when we look at the K value, we're going to see huge range. You know, K is going to range from extremely large numbers to extremely small numbers. Orders of magnitude range. And so when we look at the Ks, this is what we observe for the magnitude of the K values. And that is, if K is greater than, let's say, 10 to the 10, this is about right, 10 to the 9. You know, if K is greater than 10 to the 10, then you say that the products over the reactants is a huge ratio, which means it's almost entirely all product. You know, this is like like something like 10 billion to 1, you know, if it were, you know, it's tricky because we have the squared terms and whatever else. But it's like 10 billion part. This is like, you know, roughly the product over reactant ratio. And so in our jargon, what we say is if K is greater than 10 to the 10, then this is pretty much a one-way reaction. It's going to go all products, right? And so in Chem 1A jargon, we say, you know, complete reaction. For sure. Now, if K is less than, you know, 10 to the minus 10, what does that tell you? It's all reactant. How much product formed? Barely anything, you know, just a little tip. And so this is pretty much, in Chem 1A, we call it no reaction. The reason I put Chem 1A here is because in Chem 1B, it doesn't matter what K is. We're going to do an equilibrium, an ice calculation for all of these, right? Now, when it's in between here, you know, when it's in between here, then we have, you know, partial reaction. And so if we have partial reaction, then a Chem 1B style calculation is mandatory. And so for Chem 1A, you know, the types of stoichiometry problems that we did were where we had complete reaction or no reaction. And we avoided these. You know, these ones in the middle, we just said, oh, you know, those partially ionize, or those partially hydrolyze, or those partially react, right? And so here, partial reaction, Chem 1B calc mandatory. Chem 1B calc mandatory. Mandatory. Whereas, you know, up here and down here, well, we can probably get by with a Chem 1A style stoichiometry calculation. But for us, we're going to do Chem 1B calc for all of these. Let me put a little asterisk there. For all of these, in the end. We make some simplifying assumptions to ease our calculations, which we do, but ice for all. So you look at this K, well, you got a K about 1. With a K about 1, what does that tell you? It's kind of a fairly even mix of reactant and product. And so if we've got a fairly even mix, then what should we guess for our K? Maybe half? Half of it? I mean, or X. And so, you know, for the X, I'm going to just guess X is equal to, well, halfway between is going to be 0.05. Okay, and now let's check it. When I check, I leave the equation like this. Well, maybe I'll simplify it a little bit. You know how I'm going to simplify it? I'm going to do it like this. 1.48 is equal to, let's do this, 4x squared. It's going to be 4x cubed. I'm going to leave this as is, so I don't want to do extra work. 0.200 minus 2x, 0.100 minus x. Okay, this is going to be squared. All right, so what we're going to do is we're going to put on 0.05 here. Are you good with your calculator? Okay, put on 0.05, cube it, times 4 divided by parentheses 0.2 minus 2 times that is 0.1. So this is 0.2 minus 0.1, which is going to give me 0.1 squared. And then this is going to be 0.05 times 0.05.
Oh yeah, if you forgot your rules of exponents, you'll be doomed.
I'm sorry?
If you forgot your rules of exponents like I did, you wouldn't be able to do this problem correctly.
Yeah, so you know there's a math review. Appendix A is math. Appendix A is successive approximations. Appendix B is math review. So go back and go through. The math review is good because we need logarithms in this. Natural logs, logarithms, that kind of stuff. And so read the appendices if you want to brush up on your math.
I know, because I thought it was like 2x cubed, but when you said it was 4x cubed, I was like, I remember.
Okay. Good. Yeah, a lot of people forget to square everything inside the parentheses, including me. I do that all the time. What does it come out to? It came out to 1. So we're a little bit too small. So what should we do? Maybe, it looks like the numerator is bigger, so maybe we'll bump it up a little bit.
About 0.055.
We don't want to go two sig figs yet. We want to keep just to 1 sig fig to keep the math. And then as we continue on, we'll get more and more. But let's just try 1 sig fig. So what was it? X is equal to 0.06 or 0.07? What do you want to do? You want to do 0.07? Let's do 0.07 because that will keep the calculation quicker until we get closer, and then we'll start narrowing it down. What did you get? 12.7. Oh, that's too big. You know, when x is equal to 0.07, it's way too big. So it's supposed to be 1.48 is equal to 12.7. So it's too big. And so let's go smaller. Maybe you're right, Kelly. Maybe it was 0.055. Maybe we should go to 0.06, but 0.06 is still, I have a feeling 0.06 is still going to be way too big. Way too big. And so maybe we should go to 0.051 or something like that. You know, because we're so close. And so maybe, let's try 0.051. But here's more punching with your calculator though. 1.12?
We're getting closer.
Yeah, that's getting 1.13. All right. Yeah, let's bump it up. What do you want to bump it up to? So, okay, we went to 1, and then it went to 1.13. We need to go to 1.48, so maybe we'll bump this up to 0.05.
3.
Maybe more than that. What do you think? 5? Maybe that's too much. 4? Okay, let's compromise. Let's do 0.054. Oh, you already did it? 5.5? Oh, we'll write it down since you already did it. 0.055 gives you what? 1.83. 83, too big. And so 0.05.
3.
Well, now let's think about this more because this is 83, that's 1. We're 55, we want 148. So it's about halfway between there. So 3 or 2. 2, 5. But we'll go with 3, you're right. 4 would have been too big, probably. $1.43. Ooh. Is that close enough? Is that no? That's not close enough. It's not close. It's close. I mean, almost at 148, but not close enough. It's not close enough because one, you know, this is to 3 sig figs, so we should match it at least to 3 sig figs before we stop. And two, well, actually, we're at 3 decimal places. Now we're going to go 4 decimal places probably. But, okay, let's try it. 0.052. Oh, actually, no, this is too small. So 0.0532? 3? All right, whatever you want to do.
1.49.
1.49, is that close enough?
Yeah.
No. No, because we want to get at 148, or at least a round of 148. 149 doesn't round.
What's 1486?
1486. Let's do that. 1486. Oh, it's getting better. But let's get it so that it rounds to 148. And so 0.053. We're too high. Just a touch. 2.5. You think? 2.8. 2.8. All right. 2.8 sounds good. Okay, now this is good. All right, this one rounds to 148, right? So that's good. And 2, we're way more decimals than we're allowed. How many decimal places are we allowed? We're only allowed 3, and so we always want to carry 1 over. So we want to go 4 minimum decimal places, but we want 5. And so we're okay here, but you know, we just want. And so where do you stop? Where you stop is when you're starting to add way too many decimals than you're allowed and you got to round them anyway, right? Or you stop when it rounds to your K. Okay. Is this the exact answer? No, but it's close enough, right? For us. And so this is successive approximations. And you go, why do you have to do that? Because, you know, with a programmable calculator, you just do it easily, right? With equation solver. But the reason you have to do this, or the reason you have to learn this, is because we do this all the time. You know, approximation, think back to Schrodinger equation. Schrodinger equation can only be solved exactly for the hydrogen atom. Any other atom you have to use approximate. Now, there are a whole bunch of different approximation methods that you can use that differ in their rigor. And they're all approximating orbitals, you know, orbitals using mathematical functions. And how many mathematical functions do you use to describe the orbital? And the more accurate, but the more difficult the calculation, obviously. And so we have to use these all the time. So the reason for bringing this up now is, yeah, if you're uncomfortable doing these, then you got to start getting comfortable because your life is going to be, at least in your life, you're going to have to deal with a lot of these, and then you have to put some kind of judgment call on these sometimes. And anyway, so what we got is we got that x is equal to 0.05328. And so this is the reason why I gave about 10 minutes. I gave about 10 minutes because that should be about enough time to do enough guesses and checking or so to figure out what x is. I didn't ask you to calculate the equilibrium count, I just wanted x. And so we got x. Now what we're going to do is we can finally figure out what the equilibrium concentrations of this is going to be. And then we can figure out how much reaction we're going to have. And so this is going to be 0.200 minus. Now I like to keep it in line here so I can keep track of sig figs. And so we got to double this. And so double this is going to be 0.1. What is it? 0.10656. Is that right? 10656. Is that right?
Yeah.
Okay. All right, so I need to add a couple of zeros here just to do the subtraction. So this is going to be 4, 4, 3, 9, 0. 0.09344 molar. What is the percent reaction? If you look at it, we start off with 200 parts, we lose 106. So the percent reaction is going to be about 54% reaction. See that? A little more than half reacted. All right, over here, this is going to be 0.100 minus 0.05328. So let's carry a couple of extra zeros there. It's going to give me 2, 7, 6, 4, 0. 0.046 sub 72 molar. I carry extra digits here, and you'll see why I carry extra digits in just a second. 2x is 0.10656. How many sig figs are we actually allowed? Not many, actually. Molar. And then x, actually we only had 3 for the 148, so I'm doing too many. Let me subscript these, 5, 6. Something like this. And x is 0.05328 molar. And so when the reaction's done, this is completely done now. Only 50%, a little more than 50% actually reacted. So this is what we call a partial reaction. And this is what we expect stoichiometrically. We're going to have a lot of leftover reactants. This is a dynamic equilibrium because the reaction never stops. There are always collisions. It's just going back and forth, and this has reached the stable, what we call equilibrium. But the thing is, we have one more thing we need to do. The one more thing we need to do is a simple check. We call this the double check of our answer. What we're going to do is we're going to double check these concentrations to make sure that they give us this ratio. And so in the double check, I know that Kc is equal to 1.48. It should be 1.48. And so what I'm going to do is I'm going to plug in these concentration values and just make sure that I get that ratio. And so let's go 10656, and this should be squared. Oops, 2x. Oh, it is. Do I have to, wait a minute, don't I have to multiply this by 2? No, I don't multiply by 2 because really it's the copper plus concentration squared. Oh, Raheem. Okay, we'll stop for a moment and let Raheem speak.
Okay, so hello everybody. So